Hello and welcome back, my dear students. So after we're done with section 11.1 about the vector valued function, we're moving today to section 11.2 about the calculus of vector valued function. So basically, you're going to learn how to deal with vector valued function as a function where we need just to check the limits, the derivative, if it's continuous or not, its integration, so all the topics related to calculus. Now, as a starting point, we need to look at the definition of the limit for the vector valued function. So if the vector valued function, as we know it from 11.1, it looks like this function. R of t is a vector, basically. F of t, g of t, h of t. What should be the limit of r of t? The limit of r of t as t approaches to a, it's equals to the limit of this vector. And then it looks like that I'll take the limit for one by one of each of these three components. So it's the limit of f of t, limit of g of t, limit of h of t. Under one condition that the limit exists for all of them. So if one of them, or for one of them, the limit does not exist, then the overall limit should be, again, does not exist. So let's start with simple question, something like this. I need to find the limit for this vector valued function. So what do I need to do in this case? I'll try to find the limit for one by one. So this is equals to, I'll just have the limit inside this vector. So this is equals the limit for t squared plus 1 as t approaches to 0. The second limit, or the limit for the second component, 5 cosine of t as t approaches to 0, and the last one is the limit of sine of t as t approaches to 0. Now deal with them one by one. Let's see the limit for the first one. So the limit for t squared plus 1 as t approaches to 0, so this is 1. I'll check the limit for the second one. 5 cosine 0 is 1, so this is 5. And for the third one, sine of 0, this is equals to 0. So the limit for this vector valued function equals this vector 1, 5, 0. Does the limit exist? Yes, because it exists for all of them. So overall, yes, the limit exists and equals 1, 5, 0. The vector 1, 5, 0. Let's try one more. Something like this. I need to find the limit for e to the power of 2x. Remember, the first step, just have the limit inside for all the three components. So this is basically the limit for e to the power of 2t plus 5. And then the limit for t squared plus 2t minus 3. And the limit for 1 over t. And all of them as t approaches to 0. Okay, let's try to deal with them one by one. The first one, it's e to the power of 0 plus 5, so this is 6. The second one, as t approaches to 0, this is negative 3. What about the last one? Remember, what I'm doing is direct substitution. If I have an issue, then I'll deal with it. So this is 1 over 0, so this does not exist. So this limit, the last one, does not exist. This is basically equals to 1 over 0, so it's infinity, okay, or minus infinity. It depends where do we take it, from the right or the left, but in general, the limit does not exist. So what should be the overall limit? So hence, the limit for r of t, the vector valued function, does not exist as t approaches to 0, does not exist. Okay. Now, after we're checking the limits, okay, and if it's convergence or if it's exists or does not exist. Usually the next concept when you studied calculus, you cover the limits. The next one we talk about the continuity, if the function is continuous or not. So the vector valued function is continuous at t equals to a whenever, just the normal definition you know about the limit, that the limit should be exist and equals to r of a. So the limit of r of t as t approaches to 0 should be exist and again equals to r of a. This is when we say it's continuous. Just same thing as you covered in your calculus one. Now this theorem says what? This is an easy one. They tell you just that the vector valued function r of t is continuous at t equals to a if and only if all of its three components f, g, and h are continuous at this point. So that means I need to check one by one, just as we did with the limit. I need to check if each one of these three components, each one of these three functions is continuous. Okay, in order to have the overall r of t to be continuous. Okay, let's check the continuity for some questions. Something like this. I need to check the continuity for one by one. So let's start with the first function, f of t. It's equals to e to the power of 5 of t. This is a function, the exponential function is one of the good functions that it's continuous everywhere. We have no issues. This is continuous for all real numbers. It has no issues, continuous everywhere. Now I'll move to the second function, g of t, which is equals ln t plus 1. Okay, the ln usually has something special about the ln or the log functions, that always anything inside the ln or the log should be greater than 0. This is the only time that it's defined. Remember, even if you think about the ln function, the graph, so it's defined only for positive x. This is ln of x. So whatever inside the ln should be always positive. So that means the domain should be only at t plus 1 greater than 0. So this is continuous for what? T plus 1 should be strictly greater than 0, which means what? That t should be greater. This implies that t should be greater to 1. Okay, this one was only all real numbers. This is t greater than 1. Still, I need to check for the third one. Do them one by one and then see at the end what to do. h of t. h of t is cosine. Oh, this is our lovely function. The cosine is what? Continuous everywhere for all real numbers. So now what's the overall result? What can I say? So I can say that hence r of t is, we always take the intersection between the three domains. So this is r, okay, it doesn't affect. So what controls the domain is this one. So the domain for r of t is continuous. We'll take it from where? T greater than 1. So from greater than, this is -1, by the way. This is -1. So it's continuous from -1 to infinity. This is its domain. This is where it's continuous. From -1 to infinity. Okay. So for continuity, we need to check one by one. Many of these functions, they are like famous to you. So you know directly, like trig function, sine, cosine, they are continuous everywhere. Exponential, continuous everywhere. Len, it has an issue at the whatever inside the len should be always greater than 0. Let's see another group of functions. Something like this. What do we have here? We have tan, we have absolute value, and we have rational function. So let's try to deal with them again, like one by one. Okay? So I'll begin with f of t as tan of t. Okay, the tan is a special function. So what do we know about the tan function? The tan is continuous. Remember, when you graph the tan function, it's always good to know all of these parent graphs. So the tan looks like, the first region looks like x to the power of 3. And every time at pi over 2 you have a vertical tangent, and then you have pi. We have something similar to this again, and then one more time you have 3 pi over 2 with another vertical asymptote, and you keep repeating the same thing all over again. So anytime you have multiple odd multiples of pi over 2, the function will be undefined. The function will be undefined. So the tan x is continuous for all real numbers except, so for all real numbers except at what? The odd multiples of pi over 2. We usually write it as 2n plus 1 over 2 pi, where n belongs to z. It's an integer number. N is an integer number. So you see, just we say that, or we can say that t does not equal 2n plus 1 over 2 pi. Okay, the odd multiples of pi over 2. If you feel not that confident about writing it as general form, but just like dealing with sequences, so either you list the terms or you use the general form. So I could say that t does not equal to this value, or I can say that t does not equal all the odd multiples, which are like plus minus pi over 2, plus minus 3 pi over 2, plus minus 5 pi over 2, and the 3 dots. So it's up to you. Just write one of these two forms, either general form or you list the terms. Okay, this is for the tan, the first function, the tricky one. Now the second one, I have g of t as the absolute value for t plus 3. And we all know that the absolute value is continuous everywhere. It has no issues. This is continuous for all real numbers, so we have no issues. Lastly, I need to discuss h of t, which is a rational function, 1 over t minus 2. And we know anytime we have a rational function that the denominator can't be equal to 0. We can't accept 0 in the denominator. It will be undefined. So basically, this is continuous for all real numbers except at the value which makes the denominator 0, which is 2. So everything except 2. Now, how do I write the final result? So I can say that hence r of t is continuous for r except what? What's the excluded points? Except 2 and all the odd multiples of pi over 2. Either you write the general form or you list the terms. 2n plus 1 over 2 pi. For n, an integer number. For okay. Anyway, I don't know. It's gone. Okay. So this is continuous for, we said at r except 2 and 2n plus 1 over 2 pi for n belongs to z, all integer numbers. Okay, that's it. So let's try one more. I know sometimes there's some students, they have some difficulties with continuity. That's why I'm trying just to add a bit more functions with different types of component function. So I try to include absolute value, tan, sine, len, rational. Let's see the next function. This example. I need to determine the values for t of t for which the vector valued function is continuous. Okay, I'll deal with them one by one, just as we did before. So I need to begin with f of t. This is a square root of t minus 3. What do we know about the square root? Whatever under the square root should be always greater than or equal to 0. So this is continuous for t minus 3 greater than, with equality here, okay? T minus 3 greater than or equals to 0, which means for what t greater than or equals to 3, okay? That's the domain for the first function. Let's try with the second one. This is 1. Now 2, g of t, which is len, let's go a little bit down, 2, g of t equals len 2t plus 1. We just already discussed the len in the previous example. So this is continuous 4. You see, whatever inside the len should be greater than 0 strictly. You see the difference? With the radical, there's a possibility for equality. With the len, no. So this is for 2t plus 1 greater than 0, which means that t is greater than negative 1 over 2, okay? This is the second domain. Now I need to consider the last one, which is the good one. This is sine. So sine of t is continuous everywhere. It's continuous for all real numbers. So it has no issues, no problem for us. Now, anytime you need to find the overall domain, you need to think about their intersection, okay? So hence, r of t is continuous for what? Think about this. Let's try to use the number line as a help. It's always helpful to use the number line, especially with any inequalities domain. So the first inequality, it's greater than or equals to negative half. So this is somewhere this side. And the second one, t greater than or equals to 3. Let's say this is a 3 included. Remember, if it's not included, I'm using an open circle. If it's included, it's closed circle. So this is a 3, and again, x is greater than 3. This is greater than negative half. Now look at the intersection. Where's the intersection between these two domains? So the intersection should be somewhere here. This part. So it's continuous for the intersection, which is starting from 3 up to infinity. Okay, it's not necessary to show the number line, but it's really helpful. Always, as an intersection, it's very nice to use the number line to, especially with inequalities, to see where do they intersect. Okay, so now we saw the idea of limits, we saw the idea of continuity. Now we'll move to a part which is much easier. About after we're done with limits, continuity, now we move to if it's differentiable or not. So they are telling me that the r of t, the vector valued function, is differentiable, okay? At t is equal to, at t equals to a, and we use the general, you know this form, the general form of the first derivative. So it's the limit of r of t plus delta t minus r of t over delta t as delta t approaches to 0. And you don't need just to follow this general form. You need just only to use the basic rules that you already know about, the differentiation rules. So r prime is basically equals to what? F prime of t, g prime of t, h prime of t. So that means you need to find the derivative for each and every component. That's it. That's all. This is the derivative for r prime. Something like this. So they give me r of t and they ask me to find the derivative, which means they need the first derivative. So I need to find what's r prime of t. So basically what you need to do is just find the derivative for the components one by one. So the first component, it's sine t squared. What's the derivative for sine? It's cosine t squared. And remember, anytime you have anything in the angle other than t or x, you need to use the chain rule. Times the derivative for the angle, which is 2t. So this is the derivative of the first component. Now I'll move to the second one, this one. E to the power of cosine, same idea. So this is e to the power of cosine of t times the derivative of the angle. This is a composite of functions, so you need to include the derivative of the power, sorry. So this is negative sine of t, e to the power of cosine t. And the last one here, it looks like what? U times v. This is like product of two functions. So what should be the derivative? Derivative of the first, which is 1, times the second, so this is now len of t, plus you leave the first derivative of the second 1 over t. And if I need just to simplify this little bit, so r prime equals 2t cosine t squared negative sine t e to the power of cosine t, and the last one is, let's write the one first, 1 plus len of t. That's it. This is the first derivative for this r of t. Directly, nothing is difficult. Now there's some properties for the derivative. Just it's similar to the one that you know from Calc 1, with some exceptions. So they are telling me that d over dt for the summation of two vector valued function, so you can distribute the derivative over the addition. If I have a constant times a function, then the derivative will be c r prime. These are same from Calc 1. If I have the multiplication, you see these are 3. So if I have a function, okay, function only f of t, one component times the vector valued function, or two vector valued function dot product, or two vector valued function their cross product, what should be the derivative? It always reminds you of the product rule. If you think about it this way, remember the product rule. So if you have u v prime, so this is equals u prime v plus u v prime. If you look here at all of them, all of these three, they should remind you of this rule. But every time you consider the starting operation. So this is dot product, so I'll use dot product. This is cross product, I'll use cross product. But it's easy just to use this formula for the product rule for differentiation. Okay, now there's another definition that we need to see here, which we call the curve as smooth curve. So when can we say that any curve is smooth? So the condition for smooth curve, just like polynomials, we know that polynomials are smooth curves. So the condition that we need to check in order to show that any curve is smooth, we need to see that r prime is continuous. R prime is continuous, and that r prime does not equals to 0, except some possible any endpoint of the interval. So they will give you an interval where it's continuous. R prime should not be equals to 0, except and only maybe the endpoints of the given interval. And it's always, since we're talking about r prime, so basically I need also to show that r is continuous to be differentiable. So I need to show that r is continuous, r prime is continuous, and I need to show that r prime of t does not equal to 0. All of these three conditions implies that this is a smooth curve. We call it smooth curve. Let's see the next question. So what do we need to check? We need to check r continuous, r prime continuous, r prime does not equal to 0, except for specific points. So this is the question. We need to do what? We need to determine where this plane curve traced out by the vector valued function is smooth. Okay, so this is what we have to show, that it's smooth. So basically I need to show again, r is r and r prime are continuous curves. And I need to show that r prime of t does not equal to 0. Okay, let's try. So the first thing, I think about r of t. It's equals to what? T power 3 and t squared. What do you think? Is it continuous? T power 3, t squared, both are polynomials. So this is continuous for all real numbers. Why? Since t squared and t power 3 are continuous polynomials. Continuous polynomials. We know them. T squared, T power 3 are already continuous polynomials. So that's it. It's continuous everywhere. So the first condition is satisfied. Let's check the second condition. I need now to try r prime. So r prime is equals to what? Find the derivative. This is 3t squared 2t. And this is again for the same reason. So this is continuous for all real numbers. Why? Again, since 3t squared and 2t are continuous polynomials. So both are continuous polynomials. So they are continuous everywhere. So now r continuous, r prime is continuous. Now the only part left for me is just to show that r prime does not equal to 0, except for specific values. So let's see, what's r prime? When does r prime equals to 0? So if I think about r prime of t equals 3t squared and 2t, this is supposed to be equals to 0. So that means that both components should be equals to 0. So 3t squared equals to 0 and 2t should be equals to 0 in order to get the 0 vector at 0, 0. Okay, so let's try. When the 3t squared equals to 0, that means that t is equals to 0. And 2t equals to 0 when t equals to 0. So it seems there's a common value that makes this completely 0. So I need the only value that makes both equals to 0. Both components. So at t equals to 0, r of t should be equals to 0. Okay, so what can we say? Our conclusion should be, hence, r of t is smooth, okay, is a smooth curve everywhere except where? Except at t equals to 0. So I could write it as what? From negative infinity to 0, union from 0 to infinity. This is the interval where this curve is smooth. Everywhere except at 0 only, at t equals to 0. This is the interval of smoothness, where the curve is smooth. So you see, I accepted this point. It's only at one point. Everywhere else, it does not equal to 0. So it's only equals to 0 at one value. And it's continuous everywhere. Okay. Now, if you look at the curve for this vector valued function, it has some sharp point at 0. So that's why it's not smooth at that side, at that point. Now we have one extra theorem which says what? That the magnitude, now remember it's a vector, still dealing with vector. So the magnitude of r of t is equal to a constant value. So it's a constant if and only if r of t and its derivative are both orthogonal for all of t. So it says that like the magnitude of r of t equals to a constant if and only if, remember we use the double arrows, if r and r prime, what does it mean if they are orthogonal to each other? Remember, in terms of vectors, when do we say that two vectors are orthogonal to each other? So if I have like v and u are orthogonal to each other, so I mean that u dot v equals to 0, the dot product. Same thing here, so I can say that r of t dot r prime of t, this should supposed to be equals to 0. If I think in their graphs, what does this theorem say? So in two-dimensional space, if I'm dealing with only two-dimensional space, so it says that this theorem means that the path traced by our r of t lies on a circle centered at the origin, okay? So this one, the magnitude, if it's equals to constant, so it's basically r of t lies on a circle centered at the origin if and only if the tangent vector, remember these are vectors, the tangent vector is orthogonal to the position vector. So r of t is the position vector, r prime is the tangent vector. And when we say orthogonal, that means their dot product equals to 0. Okay, so that's it. In the three-dimensional space, so we're not dealing with circles, we're dealing with spheres. Okay. Now we think about the idea of integration. The last part of this section is to deal with integration, which is the antiderivative. So if I need to find the integration, it's exactly what you think. So you will do what? We'll have the integration inside and we'll do the integration for 1 by 1, 10 by 10. Something like this question. They ask us to do what? The integration for this vector valued function. So basically what I'm going to do, I'll have the integration inside. So this is the integration, this is indefinite integral. So this is t squared plus 2 dt, comma, the integration of sine of 2t dt, and then the last one is 4t e to the power of t squared dt. Now I need to use or to deal with the integration one by one. The first one is the easy one. This is 1 over 3 to the power of 3 plus 2t. No need to use the constant now. I could keep the constant outside at the end. Okay, so I'm not going to add the constant for these terms one by one. The second one, it's sine 2t. So the integration should be negative cosine 2t with the derivative of the argument. So this is half. So negative half cosine 2t. The last one is what you can use the u substitution. This one is with u substitution. So this is t squared, the derivative is 2t already here, but I have only additional 2 outside. So this is 2 e to the power of t squared. This is by u substitution. Finally, I can add the constant term. You could write it as c1, c2, c3. This is the constant term. Okay, so that's it. Or I can write only plus c, but that's c. So this is plus c1, c2, c3, which is the constant term. This is the part about the integration. If the integration is definite, so it's just same like the normal calc. You do the integration and then you replace the boundary for the definite integral. Something like this. If I have a definite integral, same thing. I'll take the integration one by one and then I'll replace the boundaries for the integration. So let's say if I have this question, so I'll do what? This is equals to the integration. I'll start inside from 0 to 1 sine pi of t dt, and then the integration from 0 to 1 6t squared plus 4t dt, and then I'll close the vector. Now I'll find the integration for 1 by 1 of these. So this is equals the integration. For this integration, sine, it's negative cosine, derivative, so it's negative 1 over pi cosine pi t. And I'll take the boundaries from 0 to 1. And the second one, it's supposed to be 2 to the power 3 plus 2t squared. Again, I'll replace from 0 to 1. Remember, when we replace, you replace the upper bound minus the lower bound. So this is equals to, you replace with 1, so this is negative 1 over pi cosine pi minus, now I replace 0, minus minus positive, 1 over pi cosine is 0. Okay, you do this calculation. Now the second one, same thing. So this is at 1, so this is 2 plus 2. Minus, you replace at 0, this is 0. If you do this calculation in simple, this is equals to what? 2 over pi 4. This is cosine 0. Cosine pi is negative 1, so this is 1 over pi over 2. This is already 1 over pi over 2. So it's 2 over pi 4. This is the value for the definite integral. And that's it about section 11.2, and we're done with the part required from chapter 11. Next time we'll start just to move to chapter 12 and 13, and basically you need one section each from each one of them. So that's it for today. See you. Take care.